Okay, so our focus for today will be probability, chapter 6. So when we think about probability, we have to also consider how research begins with a general question about an entire population. So a group of people who represent who we're trying to study. So actual research is conducted using a sample from the population that's being studied. Whenever we have inferential statistics, those inferential statistics use data, sample data, to answer questions about the population. So our sample of participants help us make generalizations about the population at whole. Relationships between the samples and population are defined in terms of probability. So how likely does this sample represent the population at whole? So we've got our inferential statistics that tell us about the population and our sample that gives us probability. When we have several different options, outcomes that are possible, that's how we can define probability. The probability of any specific outcome is a fraction or a proportion of all the possible outcomes available. So the probability of A equals the number of outcomes classified, whatever is classified as A, over the total number of possible outcomes. You can see that lowercase p is the symbol for probability, and the probability of some specific outcome is specified by P in that event. So the probability of drawing a red ace from a standard deck of playing cards could be symbolized as P red ace, the probability of a red ace. Probabilities are going to always be proportions. So the probability of a red ace is equal to 2 out of 52, which then tells us that the proportion is 2 red aces out of 52 cards, because a standard deck of cards has 52, and then there are 2 red aces in a standard deck. When we have random sampling, we have a sample that's obtained by a process that can ensure each individual in the population has an equal chance at being selected for a study. That is simple random sampling. And also it can tell us that the probability of being selected must stay constant from one selection to the next when more than one individual is selected. That is known as independent random sample. So this requires sampling with replacement. So whenever we have a research study, we want to give every person in the study an equal chance at being chosen. Random sampling is required in order for our definition of probability to be correct. And then the term independent is often omitted, so it just is usually called random sampling or random sampling with replacement. So you got to make those groups as equal as possible. Probability usually involves a population of scores that can be displayed in a frequency distribution graph. You can have different proportions of the graph represent different proportions of the population, and those proportions and probabilities are equivalent. A particular proportion of the graph can then correspond to a particular probability in the population. So if we look here, we have a frequency distribution histogram, and we can look at how frequent, how often this thing that we're looking for occurred. So here's our first learning check. A deck of 52 cards contains 12 royalty cards. If you randomly select a card from the deck, what is the probability of obtaining a royalty card? So we know that our total number of cards is 52. So we know that that bottom number has to be 52. So how do we figure out how likely it is that we'll pull a royalty card, one of the 12 royalty cards? Take a few moments and think of the correct answer. And hopefully everyone said B, 12 out of 52. Because there are 12 royalty cards, you have a 12 out of 52 chance at pulling one of them. Here's another learning check, true, false. Choosing random individuals who walk by you yields a random sample, and probability predicts that what kind of population is likely to be obtained. Give you a few moments to think of the correct answer. And we've got false and false. Not all individuals walk by, so everyone wouldn't have an equal chance at being selected. And then the population is given. Probability is going to predict what a sample is likely to be. Now let's go on to 6-2, which is probability and the normal distribution. The normal distribution is a commonly occurring shape for population distributions. It's symmetrical, with most of the frequency, most of the data being in the middle, with the lower frequencies tapering off towards the end, towards the extreme. It can be divided by an equation and can also be described by the proportions of area contained in each area. Z-scores are used to identify the different sections of the normal distribution. So here is a standard normal distribution. I'm sure you remember seeing this from your general psychology course. So when we look at those z-scores in the normal distribution, you can look at those standard deviations and how frequently they leave the mean, the middle. The mean is right there in the middle. And then we can see what one standard deviation above the mean or below the mean is, 2 standard deviations above or below the mean, and then 3 standard deviations above and below the mean. Sections on the left side of the normal distribution have the same area as the corresponding sections on the other side. Because z-scores define the sections, the proportions of the area apply to any normal distribution. So regardless of the mean, regardless of the standard deviation, they're going to be equal. So you can see here the distribution of math SAT scores. The proportions for only a few selected z-scores values can be shown graphically. The complete listing of all z-scores and proportions in the normal distribution are provided in a unit normal table. And that table lists proportions of the normal distribution for a full range of possible z-score values. And in Appendix B in your book, you can see that table. Here's an example of a normal table. And this shows some proportions of a normal distribution that correspond to those z-scores. The unit normal table lists relationships between z-score locations and proportions in a normal distribution. If you know the z-score location, you can then look up the corresponding proportions. If you know the proportions, you can use the table to find the specific z-score location. So probability is equivalent to those proportions. So if we were to look at that chart and examples for 6.3a and 6.3c, we can see those distribution examples for those scores. And here's some distribution examples for 6.5a and 6.5b. So let's go ahead and have a learning check. And if you were to look at that chart, can you find the proportion of the normal curve that corresponds to a z-score being greater than 1.5? And as you can see there, the correct answer would be D. Here are a couple of other learning checks. For any negative z-score, the tail will be on the right-hand side. And if you know the probability, you can find the corresponding z-score. Give you a few moments to think about the correct answer. We're going to have false. For negative z-scores, the tail will always be on the left-hand side. So that's where the negative side is on the distribution. And then true, you first find the proportion in the appropriate column, then read the z-score for the left column. Now let's move on to section 6-3, probabilities and proportions for scores for a normal distribution. So the probabilities given in a unit normal table are going to be accurate only for the normally distributed score, so the shape of the distribution should be verified before using it. For normally distributed scores, you have to transform those x values into z-scores and then look up those proportions on the corresponding z-score values in the unit normal table. So here's figure 6.10, which shows the distribution of IQ scores. Here's 6.11, which shows the distribution, for example, 6.7. And here's the distribution, for example, 6.8. And here's finding the scores that correspond to those specific proportions of probabilities, of how we can do that. And here's the distribution of commuting times for American workers. And here's figure 6.15 showing those distribution of commuting times. So all those charts are listed in your textbook. The percentile rank of a population of a particular score is defined as the percentage of individuals in the distribution with scores at or below the particular score. And a percentile rank refers to the percentage of the distribution, and the percentile refers to a score. Probability questions can be rephrased as percentile rank questions. So here's a learning check. Membership of Mensa requires a score of 130 on the Stanford-Binet 5 IQ test, which has an average of 100 with a population of 15. So what proportion, so the standard deviation is 15. What proportion of the population qualifies for Mensa? So if you calculated that, would it be A, B, C, or D? And the correct answer would be A. Here's another one. True or false? It is possible to find the X score corresponding to a percentile rank in a normal distribution. And if you know a Z score, you can find the probability of obtaining the Z score in a distribution in any shape. That's going to be true. Finding the Z score for the percentile rank can then transform to X. And it's going to be false that if a distribution is skewed, the probability shown in the unit normal table will not be accurate. That skew throws off the distribution. And then in 6.5, when we look at inferential statistics, many research situations begin with a population that forms a normal distribution. A random sample is selected from that population, and a treatment is administered to that random sample. The goal is to evaluate the effectiveness of that treatment. Probability is used to decide whether the treated sample is noticeably different from the rest of the population. And this gives us a diagram of how probability is used based on the population and sample. You can also look at figure 6.21 to show the probability to evaluate a treatment effect, and 6.22, which can show us the distribution for demonstration 6.1. I hope this information has been helpful for you and understand the content from Chapter 6.